So we're going to start the last chapter of calculus, looking at area and volume between and under two curves. And so we've actually done this before. So I'm just going to remind you in the first lecture of what we were doing in the past when we started doing this idea of integration and what it really meant. So we were trying to find, if you think about it, area, and maybe I'll call this function f of x, and I'll call this function g of x. And we were trying to find maybe the area in this section here that wasn't something I could really use in geometry. So if you recall, we actually broke this into, when we first started, into rectangles, and we would do right-sided or inscribed and circumscribed left-sided. So we're basically doing the same thing, and so you've kind of seen this before. So what we're going to do is we're going to sum all these rectangles. So how many are we going to sum? Infinite number of rectangles. And we're going to sum the area of those rectangles. And by summing the area, we'll be able to find the area between those two curves. So the area of a rectangle is the height times the width. So the height of this rectangle is in blue, and you can see it's changing every time. So how can I describe that change? Because it's different every time, but it's always my function, my top function f of x minus my bottom function g of x. That always seems to be my height. My width, and if you recall, I always had you draw in this representative rectangle, and you'll be asked to do that for this entire chapter. My width of that is going to get thinner and thinner and thinner, and we actually called that delta x. And so what we needed to do was we took the limit as the number of rectangles went to infinity. Remember that symbol? Summation as I goes from 1 to n. And we are looking at the height, which is f at x sub I, because that's changing, minus g of x sub I. It's different every time that I hit that I. And that's my height. And we're multiplying it by delta x, the width. And so we did this over and over, and pretty soon one of you recognized, like, oh my gosh, we are just integrating. So we are integrating from a to b, where in this case a happens to be the y-axis. It won't always be. To b, and then we learned how to integrate through the fundamental theorem of calculus, the evaluation component of that. Remember, there were two parts. And we found this to be the height, which is f of x minus g of x. And it was always f minus g. In the picture, you can see that by your representative rectangle. And we change this delta x to dx. So we're going to look at this two ways in this next example. We're going to apply both geometrically and calculus about what's going on. So I'm going to draw a picture of this again. F of x equals 2. That's just a horizontal line at 2. And I want a rectangle from 1 to 4. So if I just take a look at this rectangle, I can see my height is 2. Here's my height. My width down here is 4 minus 1, which is 3. And so if I just use geometry, it's 2 times 3, which is 6. So we're just going to kind of verify this through calculus. In fact, you had a problem like this on the test when you learned how to integrate and set up this summation notation from Riemann sum. You actually did a triangle. So we're going to use calculus now to figure this out. I wouldn't use calculus, obviously, on this problem, but we just want to kind of check ourselves here and just remind ourselves what was going on. So I'm integrating this from 1 to 4, okay, from A to B. I'm always going to have to put in my representative rectangle, so I'm going to do that. And I can see that the rectangle is always a height of 2. And I'm going to subtract 0. You may seem that way, you don't really need to do that. You're exactly right. But I want to always see that I've found that entire distance, even though it might be 0. That just kind of helps me if I'm looking for a system of how to do these problems. If I do the same thing every time, it'll work out. Here's 2, integrate it, 2x from 1 to 4. So the first thing I plug in is my 4 minus 2 times 1, so it's 8 minus 2, which is a 6. So this verified my geometry on this particular problem. So that's what we're going to be doing throughout chapter 6. So we're going to do 2 examples here today in the next lecture.